So, good afternoon. This is a short revision lecture on the angle and magnitude criteria. And before we start the angle and magnitude criteria, just remember now, you'll need a ruler and you also need a protractor. This is one that I've made for myself because I've got quite a big board here and I need quite a big protractor. And these two are the things that we use to do the angle and magnitude criteria with. Right, so we're going to look at the same example we looked at a minute ago. Transfer function 100 s plus 1, s minus 2, s plus 4, s plus 6, s plus 8, and this was the root loci plot that we obtained. Now we're going to try and explain to you what the angle and magnitude criteria are and how we can use them within the context of the root loci. And so I've actually plotted this out in MATLAB. And I know that a particular point on the root loci is at minus 2.7 plus 3.6j. So I've done the root loci in MATLAB, obtained that point. So there's something unique now about if you've got a point on a root loci, if you actually know it's actually on the root loci, you can apply something called the angle and magnitude criteria to that point. It only works if the point is on the root loci. If the point was over here somewhere or down there, it wouldn't work. It only works if it's on the root loci. And the first thing we do, I'm just going to get a red pen. Got my pens here. Right, so the first thing we do would be is look at the angle criteria. So let's look at this one, angle criteria. And as it implies, this is associated with angles. So what we do to apply the angle criteria, we take a point here on the root loci, assuming it's on the root loci for the moment, and we draw straight lines to all the poles and the zeros. Remember now, the crosses are the poles, and the dots with a circle around are the zeros. That's our definition of poles and zeros. So we could now draw straight lines from the point on the root loci to all the poles and zeros. So we'll just do that quickly. So we're going to get a straight line here, a straight line there, one here, one there, and finally one there. So there's our lines drawn. Now when we come to, to apply the angle criteria, we have to also measure angles. So the pole angles we're going to define as betas, so beta i's, and the zero angles as alphas, alpha i's. And we're going to measure the angles using our protractor. So let's have a look now. So this is a cross here, so it's a pole, so we can measure the angle there. Around to this side, so measure the angle there, and we could call that, say, beta 1. So I could get my protractor, I could measure this. It's about, say, I think it's about 140 degrees. Then come on to here, this is 0, so I could measure this one. This is alpha 1. So alpha 1, I think, is more like about 110 degrees. Then I get to here, so this is a pole again, so that's going to be beta 2. I could measure that one. Let's see, beta 2, about 80 degrees. Then I could measure this one. That could be called beta 3. I could measure this one, beta 4. So for beta 4 is probably about 40 degrees. So if you use a protractor to measure the angles. Then we can put these angles now into something called the angle criteria. The angle criteria states this, that the sum of the zero angles minus the sum of the pole angles should come to exactly 180 degrees if this point is on the root loci. So we could put our angles in now. So we've measured all these angles, so we could get alpha 1, that's the zero angle associated with this one here, minus, and then beta 1 plus beta 2 plus beta 3 plus beta 4. And if we do this correctly and add all these numbers up, amazingly it will come out to exactly 180 degrees. And this is then the thinking behind the angle criteria, and this works for any point. So I can move this point around here to there, down to here, down to here, any point in this diagram. If the point is on the root loci, this equation will be true, and that's called the angle criteria. And then there's another equation called the magnitude criteria. Now this one's slightly different. What we don't know at the moment is what the gain at this point is. As you go along the root loci, the gain changes. So we'd like to know what the gain at that point is. So we could call that, say, Kp. And we can use the magnitude criteria to find out what the value of Kp is. And in this particular case, the value for Kp is .76. Anyway, so we can find the value for Kp. Now, the way we do this is we get our ruler. So my ruler hasn't got any scales on, but you need one with scales on. And you go up to the diagram now and start measuring distances. And we define the pole distances as mi's and the zero distances as mi hats, just to differentiate them. So we can now measure from there to there. So I get my ruler out and I could measure that distance, and I could call that one m1. This is a 0 here, so that's going to be measure from there to there, and that will be m1 hat. This I could then measure from there to there, and I could call that one m2, that one m3, and finally that one there m4. So I could measure these using my ruler, and then we can put these parameters then into the magnitude criteria. So what we do is, with the magnitude criteria, it's Kp, that's the gain we're trying to find. Then you've got to take any numbers on the top line here. So we've got 100 in here, so that number's got to be included. So it's going to be the numbers on the top line have to be included as well. So that's 100. If this was 10, for instance, it'd be 10. Or if it was 1, it'd just be 1. But in this case, it's 100. And then it's the next part is the product of the zero distances. So in this case, there's only one of those. So it's m1 hat. Divided by, and then underneath here now, it's the product of the poles. So that's going to be m1 times m2 times m3 times m4. The product of the poles. That's going to be m1, m2, m3, m4. And that's always equal to 1 in the magnitude criteria. So in this expression now, we'll know that one, that one, that one, that one, that one. So you can work out what Kp is. And if you ever go at doing this one, we should find that Kp is actually 1.76. That's the gain at this point here. Unfortunately, somebody's just switched on their lawnmower, so I'm going to have to stop. Right, we're back again now. Slightly not as quite as noisy, but still a little bit of noise. Sorry about that. Now, given that we've got the angle and magnitude criteria, and these can be applied now to any point on the root loci, some of the things that are interesting about the root loci is about, in this particular diagram, there's probably 3 things that would be interesting to know. The first would be the root loci crosses the imaginary axis here and actually goes unstable. So it'd be nice to know what value gain that is. And it also be value here, this root loci goes this way, and at this point it's unstable, and then it stabilises. So we need to know what the value gain there is. That would be handy to know. Say Kp2. And what the value gain here is, let's call that one, say, Kp1. Now, we can use the angle and magnitude criteria to work out Kp1 and Kp2. So let me show you how to do that next. Now, for Kp1, unfortunately, it's like there's a bit of trial and error guess method. So you have to guess where this point is. So that's an inspired guess roughly from the shape of your root loci. once you've got the shape, you've made your guess, you now have to see if this point is actually on the root loci by applying the angle criteria. When you've actually found the point, so the angle, this equation becomes true, you can then go off to apply the magnitude criteria, and then that would give you the value kp1. In this particular case, because we know where the point is, we don't have to apply the angle criteria, but we do need to know what the value of the gain here is, so we could stick the numbers into the magnitude criteria to get the gain. So let's do the first one first, this point here. So we make a guess now as to where this is, and then having made the guess, we get our ruler, and again we draw straight lines now from the guess point to all the poles and zeros. So we can do that like this. So there's our straight lines, and then we bring out our protractor and we start to measure angles. So let's have a look at our angles now, and we can measure now this angle here. So we can call that one, say, it's a pole, so call it beta1, so we can measure that angle and we see what it roughly is. It's probably about 108 degrees. So then we could measure this angle here. That's going to be beta2, that's going to be beta3, and that's going to be beta4. Remember, the poles are the crosses, and they're associated with the betas. Then we can measure our zero angle, there's only one in this case, which would be alpha1. Then we stick these angles now into this equation here, and hope it would come to 180. Now, if it didn't come to 180, it means you guessed wrong. So if it comes out a bit high, it means you're too high. If it comes out a bit low, it means you're too low. So say like this came out as 200 rather than 180, I'd know it's a bit high. So just reduce the point a bit. You've got to lose about 20 degrees in all these angles. So you can have an idea of how to do that. Then once you've done that, you could get this to within some reasonable value of 180. For exam paper things, plus or minus 5 degrees will be good enough. But you should be able to get that quite straightforwardly. Then, once you've located the point, you can then put the numbers now, measure the distances, so get your ruler out and start measuring distances. So you can measure from there to there, so measure that one, and we could call that one M1. This is another pole here, so measure from there to there. That'll be M2, that'll be M3, and that'll be M4. And then this one's a 0, so you can measure that one, and that would be M1 hat. So we could put those parameters then into this equation here and compute what Kp is. And if we do that, we find the value for Kp. Kp comes out as 9.77. I've done these in MATLAB, so there I know they're correct. And the point itself here is at 7.73J. That gives you an idea how that one, if you had to have a go at doing this one, they would be the answers. You can also find the gain here. This is another important point. As you increase the gain, this root loci moves this way. And so this is going unstable here. This is stabilizing. This direction stabilizing. That direction's destabilizing. So we can now apply the magnitude criteria to this point here. So this one's more straightforward. We know that distance there, we can measure that distance there. I'm going to rub out now the magnitudes on the other diagram. So I'll get rid of these for a second. That's all my M's gone. So I could now measure from there to there. That's from the origin to there. That's going to be 2, isn't it? So we know that M1 is in fact 2, so we can put the numbers in if you like. So we've got kp times 100, then m1 is 2. Then we can measure the 0 distance, that's that one there. And that's going to be m1 hat. So m1 hat is a magnitude, so it hasn't got a sign to it. So m1 hat is just going to be 1. So that's quite straightforward. I've got a pole here at -4, so that distance there is m2. And m2 is 4. Then we can measure this distance here. And that would be associated with this pole here, so we could call it on, say, m3, and m3 is in fact 6, isn't it? And then finally, we can measure this distance here, and that is m4, that's to here, and m4 is 8. And then we could solve then this equation for kp, and kp comes out as 3.88. So looking at this now, it goes unstable at a gain of 9.77. This point here is 9.77, and this one here is 3.88. So what this implies is that as you increase the gain, say you've got a gain of 1 or 2, the system will be unstable because root loci will be down here somewhere. When you get above 3.88, root loci will cross the imaginary axis, becomes stable. But then as you make it bigger, when it gets bigger than 9.77, it goes unstable again. So it's got a window of gain over which it's stable between 3.88 and 9.77. So in this region, it's stable, less than 3.88 unstable, bigger than 9.77 unstable as well. So this is how then you can use the angle and magnitude criteria to find out the range of gain of which a closed loop system would be stable. The final thing I want to do is to look at how we could find a particular point on the root loci with an associated value for the damping ratio. So that's the last thing to do, and we're going to do that one next. Right, our final thing is to use the root loci to find the point on the root loci where we have a specific damping ratio. So this involves using finding the value, but we have a little equation which says that cos theta is equal to the damping ratio. So for instance, if we chose the damping ratio as 0.5, we could solve the equation cos theta equals 0.5, and we find that theta was in fact 60 degrees. So what we could do now is we could take our little protractor and we could go to the diagram and we could measure now 60 degrees on here, so that's going to be there, there's the 60 there, and we could draw a line now along a constant damping ratio line. Just found my red pen. Constant damping ratio line now from the origin along here like this. And this angle now is 60 degrees. And this has the property now that anywhere along that line, the damping ratio is 0.5 because it's a constant damping ratio line. So we could try and find now the value of gain for which this closed loop system had an effective damping ratio of 0.5. So this is, again, quite nice to do. We'll be given a damping ratio, let's say 0.5, solve it for theta. Then we draw the line here at the appropriate angle, which in this particular case is 60 degrees. Then what we do is we have to, knowing the shape roughly of our root loci, we make an educated guess. Let's say it's a guess, might be there, as to where we think the point is. So again, this is a guessing method. Once we've guessed the point, we then apply, to see if the guess is correct, we apply the angle criteria. If this expression now comes out as 180, we know we've guessed correctly. If it doesn't come at 180, we can adjust it until it does. And so what we do now is go back to the diagram and again use our ruler and our protractor to measure angles. So we draw lines from the guess point to our poles and zeros. Like that. And then we take our protractor and we start to measure the angles. So it's the same basic method. So we measure this angle here. Okay, that's about 130 degrees. So that'll be θ1. This is a 0. This angle here now, let's get rid of this bit. This angle here will be α1. Then this one will be β2. That'll be β3. And that'll be β4. Then put these angles, having measured them, say β4 is about 40 degrees. Put those angles into this equation, see if it comes out as 180. If it comes out a bit high, move the point down. If it comes out a bit low, move the point up. And using this technique then, you can locate this point. Once you've located the point, we can then go back, get out our ruler and start to measure the distances. So we measure again from there to there, call that one M1, this is 0, so measure that M1 hat, this one here M2, that one there M3, and finally that one there we measure from there to there, and that would be M4. Once we've got those measurements, we can then take the M1s, M2, M3 and M4 and the M1 hat, put them into this expression and solve it for Kp. And Kp then will be the value gain that puts us at that point. And in this particular case, we could work that out. I've not actually worked it out, unfortunately. I don't think I have anyway. I think the gain actually at this point is 1.76. So I've worked out 1.76. And if you measure now from the point to the origin, which is to draw a point from that point to the origin, do that in black. So that's from the desired point to the origin. That distance there, if we measure it, that is in fact omega n. So then we know the important things, and we know what the damping ratio is, what the natural frequency is, and what the gain that puts at that point is. And so that's how we can use the angle and magnitude criteria to solve the whole range of problems associated with the root loci. So I hope you found that useful. Thanks.
Okay, so here's the MATLAB code to generate the root loci and for us to see what's going on. Here's our transfer function, 100 s plus 1, s minus 2, s plus 4, s plus 6, s plus 8. And here's the little bit of MATLAB code that does it. I've defined the poles here, A, B, C and D. They've multiplied them all together here, then defined the numerator, and then used the TF command to build up a transfer function. I've typed in ZPK, sys1, so as it prints out the transfer function, so I know I've done it correctly. And then I called up the root locus command, which will plot the root loci for me. So there's the code, there's the transfer function. If we now click on the run button, we get the root loci plot, which is here. And so this now is our root loci plot, which we can now inspect. So if we go for this point here, this is where it crosses the imaginary axis. We've got the gain of 9.47. If we then inspect this point here, that's where we've got the gain of about 3.8. And we can also move along this imaginary axis by clicking on it until we get a certain damping ratio. So if we come down here, until we get a damping ratio of 0.6. Then we get this point of minus 2.73.6 and the gain of 1.8. So it's always possible to check your answers. If you were to use a piece of code similar to this, you could plot your root loci and check your answers, which could be very handy.